Hello and welcome to Equity Education, the chemistry version. And today we're going to be looking at electron configuration. So we'll start with looking at a couple of the shapes of some orbitals, and then we'll go on to electron configuration, how you write them out. Okay, so I'd like you to open your booklets and we will get started. So you've got a task to begin with. I would like you to draw a dot and cross diagram to show the electron configuration of sodium. Okay, I'm sure you've all managed it. So we know from the periodic table that sodium has 11 protons, therefore it has 11 electrons because it's a neutral atom. So on my first shell I have 2, and then 3, 4, 5, 6, 7, 8, 9, 10, 11. 1 electron on the outer shell, and we know that's right because we can look on the periodic table and sodium is in group 1, therefore it'll have 1 outer electron. Okay, so moving on. Some definitions: ground state and excited state, or some explanations. So ground state is how an atom naturally exists with its electrons in their lowest energy possible. Excited state is when an electron occupies a higher energy level compared to the ground state of an atom. Okay, so they're just some definitions that you may come across in a book. We don't really need to go in very much detail about that at this minute. However, orbital, you definitely need to be able to define this. So orbital is a region of space around the nucleus of an atom that can hold up to a maximum of 2 electrons. So I'll read that again because this is important. So an orbital is a region of space around the nucleus of an atom that can hold up to a maximum of 2 electrons. So an orbital holds 2 electrons. Okay, so there are 4 types of orbital. So we have S, we have P, we have D, and we have F. And the type of orbital in simplified terms depends on its shape. Each orbital can hold a maximum of, and I'm going to do it in pen, red pen, 2 electrons. Okay, S orbital, so you need to be able to draw the shape. An S orbital looks like this. It's a sphere. And a P orbital doesn't look like this. Let's try that again. A P orbital alright, that's a bit better. Looks like this. So it looks like a figure of 8. So these are the shapes. And these are the shapes or the regions of space where we can find an electron, well, a maximum of 2 electrons. Okay, moving on. So, I've just got a diagram here of the different types of orbitals. So S, P, D, and F. This is what they look like. For the purpose of A level, you'll only need to have S and P drawings. Okay, so moving on. Bit of definition. So the energy levels, the principal quantum number, are split into subshells. These subshells have different energy values. These subshells, confusingly, are also named S, P, D, and F. So we've said a lot of words there, and electron configuration sounds quite difficult to begin with, but as long as you keep practicing, it starts to make more sense. Right, so we'll just carry on. So these energy levels, before we carry on, are where the electrons are going to be occupied. Okay, so completing the table. I want you to have a go at completing this table from the knowledge that you should now know from previously up on the first and second page. Okay. Alright, let's see if you got the correct answer. So, a subshell, an S subshell, contains one s orbital. We know that one orbital can hold a maximum of 2 electrons. The number of electrons in the subshell must be 2. A p subshell contains 3 p orbitals. Each p orbital can hold a maximum of 2 electrons. Therefore, we can have 6 electrons in the subshell. D subshell contains 5 d orbitals. Therefore, it can hold 10 electrons. An F subshell contains 7 f orbitals, meaning it must hold 14 electrons. Okay, so we'll carry on. So we can now start to build up a picture of what is contained in each energy level. So on our first energy level, we have one subshell, and the type of subshell is S. The number of electrons in this subshell, well, we know that one S subshell contains one s orbital from this table. Therefore, we must have 2 electrons, and the total number of electrons on the energy level must also equal 2. Okay, right, I would like you to have a go at trying to fill out this table. Maybe do it in pencil to begin with so you can rub it out if you make a mistake. Okay, now you managed to do this table, so I'll go through it. So first one I did for you, the second line, so on the second energy level we have 2 subshells. We have an S subshell and we have a P subshell. We know that an S subshell contains one s orbital, therefore it has 2 electrons in it. We know the P subshell contains 3 p orbitals, so it has 6 electrons in it. So the total number of electrons on the energy level equals 8. Okay, on the third energy level, we've been through the 2 and the 6 of the S subshell and P subshell, so the D subshell contains 5 d orbitals, therefore it can hold 10 electrons. So on this energy level, we have 18 electrons. And last but not least, you don't have to worry too much about the F subshell. You won't be asked to do it, but just to round it off, we will have, how many are we going to have? 24 plus 8, so 32. Okay, right. And as it says down here, be careful not to confuse subshells and orbitals. This is important, okay? Right, so we should have built up a picture now of how we start to fill out our electrons for each atom. So we'll move on. So electron configurations. Electron configurations show us how many electrons are in a particular atom or ion and in what region or the orbital they can be found. E.g., so if I'm going to write an electron configuration for hydrogen, it would look like this, 1s1. Okay, so what do these numbers mean? Well, this big number is our principal quantum number, which is the fancy name. But we can call it the energy level. The S tells me the type of subshell, and the 1 is the number of electrons this should be. number of electrons that are contained within this subshell. So hydrogen has an electron configuration of 1s1, which means that it has one electron on the first energy level in an s subshell, which is in an s orbital. Okay, right, what does oxygen? So if I'm going to do oxygen has how many electrons? It has 8 electrons, so I need to fill 8 electrons. So my electron configuration for oxygen will be 1s2, 2s2, and 2p4. 2, 4, 8. So that tells me that I have 8 electrons, and this tells me the position of where I can find these electrons. So I have 1 electron on the first, 2 electrons in the s subshell on the first energy level. I have 2 electrons on the second energy level and contained within an s subshell and s orbital, and then I have 4 electrons on the second energy level again that are contained within a p subshell and 3 p orbitals. Okay, we'll do lots of practice, so don't worry too much if this gets confusing at the minute. Okay, so moving on. Order of filling the shells. Okay, so this is our order. This is how we fill our shells. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, so on and so on. Okay, I'm not going to go through everything. So have a go at answering this question. Look at the pattern. Look at the order. What pattern do you notice? Okay, I'm sure you've picked up on a general pattern that we need to fill an energy level before moving on. However, you may have noticed that this pattern falls down somewhere, so if you haven't, have a quick look and see if you can figure out where it falls down. Okay, so I'm sure you've spotted it. So here in our order, we are filling 4s before 3d, and we are also filling, where are we going? So 5s before 4d, and we'll stop there. So you've noticed, I'm sure you've noticed, that we are filling a higher energy level with the 4s before we complete the 3d. So let's write that down. So we fill 4s before 3d and 5s before 4d. Okay, so why is 4s filled before 3d and 5s filled before 4d when they're on different energy levels, or they have different principal quantum numbers? So the answer is really, really complicated. We don't have to go into lots and lots of detail, but see if you can work it out from this diagram. Okay, and I'm sure you've noticed here that our energy here is going up, and you may have noticed that our 4s has a lower energy than 3d when it's unoccupied. So the electron will always try and fill the lowest energy possible when it's in its ground state. So we can write that down. So the 4s is lower in energy than the 3d when it is unoccupied. Okay, right, so we'll carry on. Right, so this gets to the important bits now. So how do you fill? How do you complete these electron configurations? And there are 3 rules. So, first of all, always fill the lowest energy orbitals first. Actually, we'll change it to subshells, otherwise it will get confusing. Subshells first. However, this falls down when we see 4s and 3d, except 4s and 3d. Okay, so that's an important point. Second, always fill the energy level completely before moving to a higher energy level. Again, except for 4s and 3d. Okay, moving on. Electrons will fill separately if there are spare orbitals of the same energy on the same energy level. This will become more apparent when we go on to the box diagrams for electron configurations. Just on that point, I'll ask a question, see if you can work it out. Why will these electrons fill orbitals separately before pairing up? Have a think about it. Okay, I'm sure you've worked that out, and the answer is because electrons are negatively charged, so they will repel from each other. So they want to be as far apart as possible. Okay, so representing electron configurations in box diagrams. Again, I will do this as an example and then you can have a go later. So we better just write down the atomic numbers. So hydrogen is 1, oxygen is 8, and scandium is 21. Okay, so we represent electrons as a half arrow. So it looks like this. In books you may see it as a double-headed arrow, however technically it really should be a single-headed arrow because a single head means one electron. Okay, so representing electron configurations in box diagrams, hydrogen has 1 electron. So we will fill, let's use a different colour pen so you can see it, 1 electron in our lowest energy possible, energy level and orbital possible, so it would go here. You can see in these box diagrams that they are all going up in energy. Yeah. For oxygen, I need to fill 8. So, according to my rules, I must fill my lowest energy level first, which I've done. I then move on and fill my lowest energy subshell, and then I move on. Now look what I do here. So I put my electrons in separate boxes. Remember, that's because they are negatively charged, so they repel. So I have 1, 2, 3, 4, 5, 6, 7. I need another electron. I can't move up to this energy level, so it goes as a pair here. Okay, for scandium. So scandium has an atomic number 21, so we have 21 electrons. Again, go through this a bit quicker. Look how I fill my 2p. So I fill them separately, then I go back. This is so you don't make a mistake by pairing them up when they shouldn't be paired. Now, when I've got to here, something slightly strange happens, as we said by our order of filling. So remember to fill for S before 3D. And you can see that it actually has lower energy, or represents as lower energy here. So I will fill my 4s, and I have 1 left over, so 1 electron goes into my 3d. Okay, so you should be able to start building up a picture now of how to fill these electron configuration box diagrams and how to write them. So over to you. Practice makes perfect. So I would like you to have a go at completing the electron configurations of sodium, carbon, iron, magnesium, sulfur, nickel. Obviously you're going to need a periodic table to find out the atomic number, to work out the number of electrons. Right, have a go. There's lots of space, so if you make a mistake, you can cross it out and you can do it again below. Okay, I'll give you 5 minutes. Okay, right, let's see how you got on. So, sodium has an atomic number 11, which means it has 11 protons, which means it also has 11 electrons because it's a neutral atom. So the electron configuration would be 1s2, 2s2, 2p6, 3s1. Carbon has 6 protons, therefore 6 electrons. I'm not going to keep saying that. So 1s2, 2s2, 2p2. Fe, 26 electrons, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Remember, we fill our 4s before our 3d. It doesn't matter if you write 3d6 or 4s2, examiners don't really bother about that, but I think this is the better way to write it round. Magnesium, 1s2, 2p6, 2s2, 2p6, 3s2. Sulfur, 1s2, 2s2, 2p6, 3s2, 3p4, and nickel, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Again, be careful and make sure you fill your 4s before 3d. It's a lot of letters and numbers and whatnot, but you will get used to saying this and writing it, I promise. Okay, so moving on. So another question, for each of the above elements, name what block they are situated in and what similarity do you notice about the block and the electron configuration. So remember, on your periodic table you have an S block, you have a D block, you have a P block, and you have an F block below. So notice which ones these elements are in, which block they are in, and what similarity do you notice about the block and the electron configuration. Okay, I'll give you another couple of minutes. Okay, so hope you noticed something. So if we have a look at this, sodium is in the S block, carbon is P block, iron D block, magnesium S block, sulfur P block, and nickel D block. And you may have noticed, if you look at the very last subshell, which is filled, S1, sodium in the S block, magnesium S2, magnesium in the S block, sulfur P4 in the P block, carbon P2 in the P block, and D6 for iron, which is situated in the D block, and nickel D8, which is also situated in the D block. So that tells us that the last subshell that is filled tells us what block the element belongs to. Okay, right, so moving on. Right, so you're doing a lot of work on this video today, so I want you to complete the box diagram for sulfur and for boron. I will give you 5 minutes. Okay, so we'll fill this out together. So I've drawn my boxes, my electronic box diagram and fill out. Don't forget to write your next to the box the principal quantum number or energy level and the subshell, so 1s, 2s, 2p, 3s, 3p. So we need to fill 16 electrons, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Remember, separately if they can, and then join up, because otherwise this would be wrong. Boron has 5 electrons, so 1, 2, next energy level, 3, 4, and 1 in the 2p subshell. Right, hope you're getting it, and we will carry on. So, exceptions to the rules. So, 2 exceptions to the rules that you need to know about. Copper and chromium do not follow the conventional system for filling orbitals. Okay, so copper has the electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s. Let's actually change colour. 4s1, 3d5. Oh, excuse me. Okay. So 3d10, not 3d5. I'm doing chromium. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Chromium has an electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p6, different colour pen, 4s1, 3d5. Okay, so why does this happen? Well, this happens because there is more stability when a subshell is filled or partially filled for d orbitals and for transition metals. Okay, it's a pretty basic explanation, and it's fine for A level. All you have to do is really just remember that copper and chromium only has one of its 4s orbitals, one electron in its 4s orbital. Okay, so moving on, so the electron configuration of ions. So the numbers of electrons that are gained or removed have to be represented in the electron configuration of the ion, e.g. So I've already written out for you, you need to copy it down. So for chromium, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Okay, remember, this is the tricky one. Cr3 plus ion, so I've removed 3 electrons, and I want you to have a look at which electrons you think I've removed and from where. Okay, as you probably noticed that the 4s electron has been removed before the 3d ones, because otherwise it would have been 4s1, 3d, I can't take that away, 4s1, 3d2. So you may notice that we always remove 4s before 3d, and again the reason why is very, very complicated, but a very simple explanation is that once the energy level, once the 4s has been occupied, I'll just show you here. So once this 4s has been occupied with electrons, it actually jumps up in energy. Yeah, so it becomes higher in energy than the 3d, which is occupied. So we remove the 4s first because it's higher in energy when it is occupied. Don't worry too much about that explanation. It will do for now, but you don't have to explain any exams. The main important thing is that we always remove 4s before 3d. Right, back to your turn. So draw the following electron configuration of the following ions. So that means you will have to turn these elements of atoms of these elements into ions before you can do this. Okay. Have a go. I'll give you, you'll probably need, I would say, 10 minutes to do this. Okay, so I hope you managed to do this. So calcium Let's quickly go through this. Calcium is in group 2, therefore it has 2 outer electrons, so it needs to lose 2 outer electrons to gain a full outer shell, so it has a charge of 2+. This is the electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6. So normally it would have had 4s2, but we have removed these 2 electrons. Okay, moving on. Exactly the same process, so K plus 1s2, 2s2, 2p6, 3s2, 3p6. Cu2 plus is a bit different, so 1s2, 2s2, 2p6, 3s2, 3p6, 3d9. Remember, that's because we have 4s1, 3d10. So I remove my 4s1 and then I remove my my one other electron from 3d, so it becomes 3d9. Okay, I hope that makes sense. F minus, so we're now adding electrons, so it was 1s2, 2s2, 2p6, and S2 minus, 1s2, 2s2, 2p6, 3s2, and 3p6. And you may notice that if you look here, 3p6, 3p6, 2p6, 3p6. So all ions, apart from transition metals, will have a completely filled subshell. Okay, so all ions have completely filled subshell, and we'll just put in brackets apart from our transition metals. And that makes sense, doesn't it? That makes sense because when we are forming ions, we have to make sure they have a full outer electron shell. So all we're saying is this subshell is an outer electron shell, which has to be completely full. Right, so another question, and then we've got some more questions for you coming up. So magnesium will react with oxygen to form magnesium oxide. Write down the electronic configuration of the cation involved in the ionic compound. Okay, I'll give you a couple of minutes to think about it and work out the answer. Okay, sure you work this out. So my ionic compound, magnesium oxide, is MgO, therefore must have a 2+ charge on the cation. Remember, the cation is the positive ion. So my electronic configuration must be 1s2, 2s2, 2p6. Remember, you have to remove the 2 electrons from the 3s2 to get my 2+ charge. Right, next, so noble gas configuration. So to save time, it is possible to use a noble gas as part of the inner electron configuration. Okay, so write out the electron configuration of argon. Okay, I'll give you a couple of minutes. Okay, so I'm sure you've written this out. So the electron configuration of argon is 1s2, 2s2, 2p6, 3s2, 3p6, and we can say that all of this is equal to argon. So if we have square brackets and AR in the middle, can be used as a shorthand for the electron configuration of any elements on the period directly below on the periodic table. And another way of saying that is the noble gas that is directly behind the element on the periodic table can be used, and we will do an example, e.g. which one should we do? Okay, so for potassium, e.g. potassium, instead of writing out 1s2, 2s2, 2p6, 3s2, 3p6, we can say that AR is equal to this, and then I just write my what my next electrons are. In this case it would be for potassium 4s1. So this means only the partial electron configuration is shown. Okay, so it's important in the exam, if you are asked to write a full electron configuration, you cannot use a noble gas configuration. Okay, only if the question specifies that you can use noble gas configurations are you allowed to use it. Otherwise, you will lose the marks. Right, just for a bit of solidation, have a go at writing the noble gas configuration for scandium, strontium and sulfur, and then we are finished. Okay, sure you did alright at this. So scandium would be argon is the noble gas, which is directly behind it, so then 4s2 3d1. Strontium we would use krypton, so 5s2, and sulfur we would use neon and 3s2 3p4. Right, quite a long one, and you had to do a fair amount of work in that one, but if you did all of them electron configurations, I can guarantee you're going to remember it. Okay, so I hope that was helpful, and I will see you next time. Okay, bye bye.